So let me start by introducing Siyao, and it's a real pleasure that you were able to join for today's talk. And the title of the talk is Mirror Diffusion of Cosmic Rays in MHD Turbulence. So Siyao is currently a Hubble Fellow at Princeton. I think you're at Institute of Advanced Studies. Her work was in fundamental physics studies of magnetohydrodynamic MHD turbulence, turbulent dynamo, particle transport in MHD turbulence, and other topics. PhD was from Peking University, and she has already received several awards and honors, including the International Union IUPAP Young Scientist Award in Astroparticle Physics, the Cecile Play-Kaposhkin Doctoral Thesis Award, as well as the IAU PhD Prize. So this is really an honor, and congratulations for that. So we should get started. Just a note, we will be recording this for our YouTube archives. And if you're not speaking, please mute yourself. So please get started.
Thank you very much, Rashmi. Let me, okay. Yeah, so yeah, just in case I don't see you raise the hand, you can just interrupt me directly during my talk if you have any.
I can do that.
Yeah, thank you. Okay, so yeah, so I will talk about this is some our recent study on a new mechanism for spatially confinement of cosmic rays and diffusion of cosmic rays in the astrophysical medium. So I would like to start this simple diagram showing the close correlation of the three: MHD turbulence, cosmic rays, and star formation. So MHD turbulence has been recognized as the essential ingredient in the modern understanding for both diffusion, acceleration of cosmic rays, and for star formation, of course. And these three are also closely related to each other. For example, we know that supernova explosions, supernova shocks, these are the very promising candidate for acceleration sets of energetic particles, cosmic rays. And cosmic rays and their propagation in molecular clouds can also affect the ionization rate, the pressure support of the cloud, and they, of course, affect the chemistry, the dynamics of the clouds, and the star formation efficiency. And MHD turbulence, they affect the cosmic rays, as we know that cosmic rays, their diffusion in space is not caused by the collision between these very energetic particles themselves, but caused by their interaction with the ubiquitous turbulence magnetic fields in the interstellar medium. So I always like to show this very remarkable two big power laws. On the left, this is the power law of the cosmic ray energy spectrum. So many of these experiments were collected since 2000. So there are a lot of new data showing more detailed information about the cosmic ray energy spectrum. It expands many orders of magnitude in cosmic ray energies. So we really believe about PeV, EeV. These are galactic cosmic rays, and beyond this energy, they come from other galaxy extragalactic accelerators. On the right, this is so-called the big power law in the sky. This is in fact, the density fluctuations induced by interstellar turbulence, and by measuring the density fluctuations at different length scales, this is also a collection of measurements of different methods. For example, this includes diffuse interstellar medium from H-alpha intensity fluctuations, and also measurements coming from the scintillation, the scattering of pulsars, nearby pulsars. And at the very small scales, these are in situ measurements by Voyager. But roughly speaking, these different measurements on very different length scales also follow nicely this so-called Kolmogorov power law. This is very characteristic power law spectrum for turbulence. This is extends from hundreds of parsec down to 10 to 6 kilometer, but now with Voyager, this down to very small scales to tens of meter even. So these two big power laws, we believe they are closely connected to each other. Cosmic rays with different energies can interact with turbulence on different length scales. For example, for GeV cosmic rays, in the typical interstellar magnetic field of a few microgauss, their gyro-radius is about a few solar radii. But if we move to higher energy cosmic rays, let's say PeV cosmic rays, then their gyro-radius in the diffuse interstellar meteor is about a few parsec. Okay, so this is for cosmic rays. For star formation, of course, we know that turbulent magnetic fields are very important physical ingredient affecting star formation. There has been ample observational evidence showing stars form in turbulent environments based on the measurements using different gas tracers in this cold interstellar phase molecular cloud environments. But here I would like to show a new observational evidence that we obtained from Gaia. Gaia provides 60 measurements of stars, including 3D velocities of stars and 3D positions. Sorry, I think there's some noise from the outside. So what we do is in several nearby star forming regions, we collect the Gaia measurements for the motions of stars. So here what I show is the velocity difference between a pair of stars as a function of their separation, 3D separation. So different colors represent different star forming regions. You can see that the star motions in young stars, they also follow quite nicely a power law relationship. So this also shows that stars form in a turbulent environment. Naturally, they inherit these turbulent motions of the gas where they form from, even after they form, this memory is still kept in their motions. So I think this is very direct evidence showing the turbulence is quite important for star formation.
So can I just ask for clarification? I don't see a clear power law for all star forming regions. I mean, I see an upward trend with the separation, but I'm a little bit, why did you characterize this 4 diverse curves as following a single power law? I'm not quite understanding this.
Yeah, so, okay. Among these different curves, we see that Orion doesn't, because it's quite flight. If there's no relation between this delta V and the R separation, it could be just like white noise. It should be flight. And this is the case of Orion because Orion has a really massive star cluster where the gravitational interaction just distort these turbulent motions when they form. But if you look at other cases, well, the levels of turbulence are not exactly the same, so they are not really overlap with each other, but they approximately follow this 1/3. This is the Kolmogorov power law scaling. So you can see they have followed some rising trend toward larger velocity difference toward larger separation between the pair of stars.
And I don't know how to pronounce it, ficus, that seems to be trending downwards above 10 parts.
So yeah, so the outer scale where the turbulence, this we believe can tell some information about where the energy is injected. So it's beyond. So usually we think that turbulence in the SM is injected by supernova explosions about 100 parsec or tens of parsec. So in different individual star forming region, the driving could be different. The driving mechanism and the energy that input the system could be different. So that can give us different level of turbulence and where the driving scale could be also different. Yeah.
Okay, thank you.
Yeah, so yeah, it's a so stars is not a really clean tracer of turbulence, unlike gas tracer. So gas tracer would give much better measurement of turbulence and also down to much smaller scales. But here it's just an illustration or evidence showing stars, they also feel the turbulence, and even when they form, they still keep some memory of the turbulent gas. It's quite natural, but maybe it's I think it's very interesting confirmation from observations. So since both MHD turbulence is important for cosmic rays and star formation, so it's not surprising to see there's a strong correlation, tight correlation between the non-thermal emission from cosmic rays, including synchrotron, this radio emission, and gamma emission, and their correlation with the star formation indicator, the infrared luminosities. You can see this is on the left, this is radio infrared, and right is gamma ray infrared luminosities for star forming regions. I would like to show another example. I think it's really nice illustration for the close correlation among the three, MHD turbulence, cosmic rays, and star formation. So this is some our recent study using the new technique for measuring magnetic fields in turbulence medium. It's called gradient technique. This is a technique based on the anisotropy of MHD turbulence, which I will talk about this a bit later. So then we trace the magnetic fields in nearby Seyfert galaxies. Here I show this one as example. And so one on the left, this is the magnetic field traced in Siyao, the cold gas where stars form. On the right, this is the magnetic fields traced using synchrotron intensity. So the synchrotron emission from cosmic ray electrons. And you can see that the magnetic fields traced by different tracers measurements, these little segments here, different colors, but these little segments show the magnetic field orientations. And you can see they agree very well with each other. The orientations of the Seyfert galaxy in the central region and the spiral arms. So this, I think, is a really nice illustration showing the close relation of the MHD turbulence, where based on H, we apply this gradient technique and we measure the magnetic fields in Siyao and synchrotron emission. So it tells us that the cosmic ray diffusion is closely related to star forming regions. So the star formation can be triggered. It can be triggered by supernova shocks, for example. So here, this is shows the cloud interacts with a supernova remnant. So in the hydronic scenario, the cosmic rays that accelerated at a supernova shock can escape and then diffuse in the surrounding molecular cloud. So these clouds depend on the source, they can be in the vicinity of the supernova remnant, or they can be already swept inside the supernova remnant. In the hadronic scenario, these clouds serve as the target gas for the proton-proton interaction and subsequent neutron pi decay. So they can be very bright gamma ray sources. And then by detecting their gamma ray spectrum, we can get information on both the spectrum of the cosmic rays and their diffusion in the molecular cloud. Here I made experiments. I used the average galactic diffusion coefficient of cosmic rays, try to model the gamma ray emission. So you can see that the gamma ray emission is very sensitive to the diffusion model of cosmic rays. So if I use this average galactic diffusion coefficient, it is quite large diffusion coefficient. It means that the particles cannot stay sufficiently long in the molecular cloud. As a result, they cannot sufficiently interact with the protons in clouds. They cannot produce sufficient amount of gamma ray flux to match the observation. The blue line is the model spectrum, which is far below the observation, the data for this particular source. And you can also see that the spectrum shape using the average galactic diffusion coefficient is also shallower than what the observation data shows. So it tells us that the diffusion of cosmic rays, if you want to understand gamma ray emission, it has to be much slower, much suppress the diffusion in these star-forming regions. So there are also many other gamma ray observations suggest the same suppressed diffusion. For example, the TeV halos, the gamma ray emission around nearby Pulsar nebulae also suggests the diffusion coefficient of cosmic rays should be smaller than more than 2 orders of magnitude compared to the average galactic diffusion coefficients. So to understand cosmic ray diffusion, we need, first step is to understand MHD turbulence. So let's first look at hydrodynamic turbulence. This is the Kolmogorov power law I mentioned earlier. This is the characteristic spectral slope of for the energy cascade of turbulence. So energy of turbulence is very similar to the waterfall. The energy is injected at a large length scale, and then it gradually cascades down towards smaller scales until eventually the turbulent kinetic energy is dissipated at the smallest length scale. And we call this inertial range of turbulence between the injection scale and the energy dissipation scale. So for interstellar turbulence, the energy injection is usually done by supernova explosions on about 100 parsec. For the energy dissipation, there are different effects depending on the local plasma conditions that can damp the turbulent energy. The physics behind this 5-thirds Kolmogorov power law is there is no energy loss within the initial range during the energy cascade. So the turbulent energy within one idiotonal time is passed down toward next smaller scale without loss of the energy. So that is for hydrodynamic turbulence. In the presence of magnetic field, we have magnetohydrodynamic turbulence. But in the history of cosmic ray study, for many decades, MHD turbulence was modeled by an ensemble of linear MHD waves. But now we know that MHD turbulence is very different from linear MHD waves. For example, here, this is example showing how different these two can be. So in this work, this has been already done, you can see more than 20 years ago. They present on the left, this is MHD turbulence. On the right, this is from ensemble of linear waves. They have exactly the same energy spectrum, this Kolmogorov energy spectrum that I just showed. But despite they have the same energy spectrum, but you can see even by eye, the magnetic field structure is very different for realistic MHD turbulence and the linear wave model for MHD turbulence. So for cosmic ray studies, they strongly depend on the MHD turbulence that they directly interact with. So we can easily understand if we study cosmic ray propagation in the wave model, the result cannot be very realistic. It cannot give us the right physical picture for cosmic ray diffusion in realistic interstellar medium. So for MHD turbulence, I mentioned earlier that it is anisotropic. So for hydrodynamic turbulence, the turbulent motions are isotropic, with isotropic energy distribution. There's no preferred direction for the turbulent motion. But in the presence of magnetic field, we know that magnetic field, they have the tension, magnetic tension, the Lorentz force. If we try to bend the magnetic fields, we would feel the resistance from the magnetic tension force. So turbulence is very smart. In the presence of magnetic field, turbulence finds a particular direction where in this direction, it can easily perturb the magnetic field without changing the magnetic field strength, without bending the magnetic field lines. And this direction is the direction perpendicular to magnetic field. I want to stress that in the original GS95 Goldrex-Rader paper on MHD turbulence, this is how the modern understanding of MHD turbulence started. They used the global reference frame of the mean magnetic field. This was a wrong reference frame when we talk about the perpendicular direction. Later in Lazar and Vishniak 1999, this was corrected. It was identified it must be the direction perpendicular to the local magnetic field in the local reference frame. So the local magnetic field is defined as the magnetic field averaged over the length scale of interest. It can be very different from the global mean magnetic field over a large length scale. Only in this direction, as I mentioned, that the turbulence can easily perturb the magnetic field, and as a result, an energy cascade is mainly going on in this perpendicular direction. The resulting turbulent energy distribution becomes anisotropic. So here I show this numerical simulation from Zhongyan Chen and Lazar in 2003. Initially, the energy is injected on large scale with isotropic energy distribution. Along the energy cascade, it gradually becomes more and more anisotropic. So with the energy cascade, turbulent energy decreases, but magnetic fields keeps constant. So the effect of magnetic fields becomes relatively stronger and stronger, causing the anisotropy also becomes stronger and stronger towards smaller scales. You can see the eddies become highly elongated along the local magnetic field at small length scales. Here is another illustration. We can do such experiment. At large length scale, we have isotropic structure. And then what happens that in MHD turbulence, we can see that this gradually becomes more and more anisotropic towards smaller scales, forming these elongated structures or filaments aligned with the local magnetic field. In this simulation, we have the mean magnetic field in the horizontal direction. But as I mentioned, these structures, they are aligned not with the mean magnetic field, but with local turbulence magnetic field. This type of turbulence is solenoidal turbulence. It is a divergence. Divergence of this velocity is free. It's very similar to the turbulence we drive in coffee with a spoon. We stir the coffee and we also drive solenoidal turbulence, and that works to mix the different fluids in the medium. In fact, in this study, the motivation was to explain the ubiquitous density filaments that we see in H1 gas in warm neutral medium that are aligned with the local turbulent magnetic field. And we see that the anisotropic MHD turbulence can naturally explain these parallel filaments in the SM. Okay, so back to cosmic rays. As I mentioned that diffusion cosmic rays strongly depends on MHD turbulence properties as this cause their diffusion in space. But it's quite complicated to describe MHD turbulence. How to quantify this strong dependence of diffusion on MHD turbulence properties? It will be quite convenient if we can find a physical parameter that can characterize property of MHD turbulence, and by finding the dependence of cosmic ray diffusion coefficient on this parameter, we can directly get information how to describe this dependence. So here, this is the fundamental characteristic parameter of MHD turbulence, the alpha Mach number, MA. Alpha Mach number is the ratio of turbulent velocity at the injection scale of turbulence and to the alpha velocity. So VA. VA is the speed that magnetic fluctuation propagates. It depends on magnetic field strength B and density of the medium. When MA is small, we have subaphanic turbulence. This means that in terms of energy, the turbulent energy is smaller than the magnetic energy in the medium. So in this case, magnetic fields are weakly perturbed by turbulent motions. So in this simulation, the thin lines represent magnetic field lines. You can see they are quite smooth with small perturbations. But in other cases, if we have MA larger than 1, we have superaphanic turbulence. In this case, the turbulent kinetic energy is larger than magnetic energy. So turbulence can easily distort the magnetic field lines. You can see in this case, the field lines becomes highly turbulent, highly tangled. Correspondingly, if we put particles, cosmic ray particles in different cases with different MA, the thick lines represent the trajectories of cosmic ray tested particles. You can see in 2 cases, the cosmic rays have very different diffusion behavior as what we expect. Okay, so now we can quantify the diffusion behavior of cosmic rays and its dependence on MA by directly measuring the diffusion coefficient in MHD turbulence. In the presence of magnetic field, the diffusion coefficient of cosmic rays is also anisotropic, and this anisotropy depends on the anisotropy of MHD turbulence. So we should separately measure the diffusion coefficient in the direction parallel to magnetic field and perpendicular to magnetic field. So I did this. This was my first project on cosmic rays 10 years ago. And more recently, Yue Hu has also did this experiment, and we found consistent result. In the parallel direction, this is the parallel mean free path, which is directly related to the parallel diffusion coefficient. It depends on MA approximately to MA minus 2. This is natural. As we increase the magnetic fluctuation toward larger MA, the scattering is enhanced. As a result, the mean free path of the particle decreases. So we see the parallel diffusion coefficient decreases toward increasing MA. In the perpendicular direction, it has even stronger dependence on MA to the force power. So before this study, in the quasi-linear theory, it was believed that perpendicular diffusion coefficient proportional to MA squared. But here we confirm that in MHD turbulence, the realistic MHD turbulence, we get stronger dependence MA to the force power for the perpendicular diffusion coefficients. So parallel diffusion comes from the interaction of cosmic rays with turbulent magnetic fields. But perpendicular diffusion is quite different. It comes from the intrinsic properties of magnetic fields themselves. So in these 3 panels, I show the superdiffusion of passive smoke particles in turbulent atmosphere for hydrodynamic turbulence diffusion, and perpendicular diffusion of magnetic field lines in turbulence, and cosmic ray particles that trace the turbulent magnetic field lines. All of them show the similar superdiffusion behavior. So superdiffusion is a faster diffusion compared to normal diffusion, the random walk diffusion. This happens because of the energy cascade of turbulence. The separation between two particles or two field lines, they experience larger and larger turbulent eddies, and that causes the accelerated growth of their separation in the direction perpendicular to magnetic field. In this particle experiment, we have the mean magnetic field in the vertical direction. So this quickly causes the faster spread of the particle trajectories and faster increase of their separations. So this is the faster perpendicular diffusion. And again, the cosmic ray perpendicular diffusion comes from the perpendicular diffusion of turbulent magnetic fields. Okay, so now we know theoretically and numerically tested MA-dependent cosmic ray diffusion coefficients in both parallel direction and perpendicular direction. How can we relate this to realistic astrophysical medium? We need this gradient technique that I also mentioned earlier, that also based on the same anisotropy of MHD turbulence. For example, this is done by Yue Hu. They measured in several nearby molecular clouds. Here, just to show this one as example, using the gradient technique to map the MA, this characteristic MHD turbulence parameter, its distribution on the sky, and different colors represent its different values. And you can see that even in the individual, the single star forming region, MA is not a constant. So because the fluctuations of different parameters, magnetic field strength and density and turbulent velocity, the MA can have different values. So if we combine the two, the MA dependence of cosmic ray diffusion coefficient that I showed and the MA distribution obtained in observations, and note that this can be done by using different gas tracers, so we can know the MA distribution corresponding to different phases of the interstellar medium. We can combine the two to get a self-consistently determined cosmic ray diffusion coefficient in star-forming regions. And this will be very important for us to understand why cosmic ray diffusion is surprised in star-forming regions, and we will be able to identify the physical reason behind this observational finding. So this is a direction that we are right now working on. Okay, the second part of my talk, I want to move on to the mirror diffusion part. So earlier I showed this turbulence in coffee, this solenoidal turbulent motions, this divergence free of the turbulent velocity. MHD turbulence has also a different type of turbulent motions that is compressible turbulence. I will show that you can see the difference between the two very easily. Different from the solenoidal incompressible turbulence. For compressible turbulence, the turbulent motions can create a large contrast of density structure. You can see that. And such turbulence in the supersonic condition can produce a lot of shocks and then create these high density structures. And they can also compress magnetic field very significantly. In fact, these high density structures are quite important for us to understand star formation, because these high densities later can undergo gravitational collapse and become seeds for star formation. In terms of star formation, the solenoidal turbulence works to suppress the star formation, but compressible turbulence, highly compressible turbulence works to boost the star formation efficiency. In terms of cosmic ray diffusion, as I mentioned that with compressions, the magnetic fields can also be compressed. The magnetic field strength now can be changed. So when the cosmic ray, so this creates this, we call it magnetic mirror structure. When cosmic ray move from a weak magnetic field region to a strong magnetic field region, it would feel the Lorentz force that try to slow it down and eventually can reverse its moving direction back to the weak magnetic field. So we see the particle can be reflected by the magnetic mirror, the compressed strong magnetic field. In fact, this is not a new mechanism. This is the magnetic mirroring effect, which is known for many decades, has been used in plasma physics, in fusion experiments, and also in literature for studying trapping of cosmic rays. But now we want to revisit this mechanism in MHD turbulence. This is a numerical experiment. This is a one particle's trajectory. Different colors represent different time. And you can see locally the particle can be confined because of the mirror reflection, and the particle can reverse its moving direction because of the mirror reflection. Corresponding to this mirror reflection, we can see its pitch angle cosine oscillates around 0, which means the particle can easily cross the 90-degree without any problem. So here the oscillation in mu correspond to repeated reflection of particle. They go back and forth between two mirror points. This gives very effective confinement of cosmic rays in space. Well, in fact, in my first projects, I already found this numerically, but at that time, it was more than 10 years ago, I thought this is some numerical glitch, but I didn't understand why particle can suddenly reverse its moving direction. But now we know this is caused by magnetic mirrors. But I would like to stress that different from the mirror trapping studied in the literature, that cosmic rays is trapped in a magnetic bottle and they don't move much spatially. But here we are dealing with MHD turbulence. As I mentioned that although in parallel direction, they can be reflected by magnetic mirrors, but in perpendicular direction, we know that turbulent magnetic fields have perpendicular superdiffusion, and the particles that trace the magnetic field lines also have the perpendicular superdiffusion. So in perpendicular direction, there's no trapping at all. As a result, we are not having mirror trapping, but we have mirror diffusion. So here, this is two cosmic ray particles. Initially, they have small separation. You can see that they follow the turbulent magnetic fields and their trajectory spread out in perpendicular direction. In the meantime, they interact with different magnetic mirrors and going back and forth in parallel direction. As a result, this gives us a new diffusion mechanism of cosmic rays. It has a very strong dependence on the pitch angle of the particle. So pitch angle is the angle between the particle moving direction and local magnetic field direction. So coming back to this observation that I showed earlier for the molecular cloud in the vicinity of middle-aged supernova remnants, these bright gamma ray sources. Now, if we apply this new identified mirror diffusion, let's see what different result it can give us compared to the standard model that I used earlier, the average galactic diffusion coefficient. Recall that the average galactic diffusion coefficient would give too fast diffusion of cosmic rays. They can quickly escape from the molecular cloud, and thus they cannot produce sufficient gamma ray flux as observations. But the mirror diffusion is quite different. They can very effectively confine the particles in the molecular clouds for them to have sufficient interaction with the protons there and produce sufficient gamma ray flux. So we can see that the mirror diffusion can give a better agreement with the observational data. And also because the mirror diffusion coefficient has quite strong dependence on cosmic ray energy. If we apply the mirror diffusion, we see it gives also quite good agreement with the very steep gamma ray spectrum for this gamma ray source. Okay, so I also want to briefly talk about the difference between mirroring and scattering. So scattering is the mechanism that has been studied for many decades. Its diffusion comes from the pitch angle scattering caused by magnetic clouds in original Fermi's picture. But now we know these are magnetic fluctuations cause the scattering of the particle and their spatial diffusion. But now we have both mirroring and scattering. Here I show the mirroring rate and scattering rate as a function of the cosine of their pitch angle. We see that mirroring has the dominant rate compared to scattering, the upper one, at large pitch angles, so corresponding to small mu. So only at large pitch angles, the particles are subject to mirroring because we need the first adiabatic environment to be conserved. But if we go to small pitch angles, large mu, then the scattering rate can go beyond the mirroring rate. So the scattering dominates over mirroring at small pitch angles. So for mirroring, we already know that it gives us very small surprise diffusion coefficient, which is quite important for us to understand the surprise diffusion of cosmic rays in star-forming regions. For the scattering particles, in the literature, the mean free path of scattering particles is calculated corresponding to 90-degree change. But here, in the present scattering, we only need the particle pitch angle to change from 0 degree to the critical angle, which corresponds to the balance between the mirroring rate and the scattering rate to give the parallel mean free path. As a result, so this is for the scattering parallel mean free path, and I derive it for faster modes, but you can see that it gives the 1/3 energy scaling. This is because when we consider you can see when we do the integral of the pitch angle, we are not doing it from 0 degree to 90 degree, but from 0 degree to this critical angle, as I mentioned, corresponding to the balance between the mirroring and the scattering. So then the energy dependence comes from not only the energy scaling of faster modes, but also comes from the energy dependence of this critical pitch angle. And combining them, it gives us this 1/3 energy dependence of diffusion coefficient, which is more consistent with the cosmic ray observation in the average galactic diffuse medium. And the scattering diffusion coefficient, it can easily determine that. It only depends on two parameters. One is the magnetic fluctuation of the faster modes, which dominate the scattering of cosmic rays. And another is the driving scale of turbulence, where the energy is input in the interstellar medium. And I also mentioned that because now we don't need to integrate the pitch angle change all the way to 90 degree, so that naturally solves this 90-degree problem, which is a long-standing problem for the linear quasi-linear theory in the literature. So at large pitch angles close to 90 degree, we have the mirroring to take care of the particle motion. And earlier I showed that the mirroring can make the particle easily cross the 90 degree repeatedly. So we naturally solve the 90 degree problem. And we also know that faster modes are more subject to different damping effects in the interstellar medium. But we know that damping is more serious for particles with large pitch angles, because to satisfy the gyrescence condition, when we go to large pitch angles, the damping becomes a problem. So now, because again, we don't need to worry about large pitch angles for the scattering, so we also can avoid the damping problem for faster modes. So now with this scattering by faster modes, under the consideration of mirroring, we get the slope more consistent with observations, this diffusion coefficient slope as a function of cosmic ray energy. We also got reduced mean free path corresponding to a smaller range of the pitch angle change. And we also naturally solve these two long-standing theoretical problems in the literature. Okay, so at the end, I come to my summary slide. I start with the close correlation of MHD turbulence, star formation, and cosmic ray diffusion. And then I talk about anisotropy of MHD turbulence. And we know MHD turbulence are very different from linear MHD waves. And this new understanding of MHD turbulence brings us new understanding of cosmic ray diffusion. Its anisotropy in its diffusion comes from the anisotropy of MHD turbulence. Cosmic ray diffusion strongly depends on MHD turbulence properties. We find a characteristic parameter MA that gives us the relative importance between turbulent energy and magnetic energy MHD turbulence. By combining the dependence of cosmic ray diffusion coefficient MA and the observationally mapped MA with the gradient technique, we can now self-consistently determine the cosmic ray diffusion coefficients in complicated star-forming environments. At the second part, I talk about mirror diffusion that comes from the compression of magnetic field. By the way, this can happen in both compressible medium and incompressible medium. In incompressible medium, magnetic compressions are done by pseudo alpha modes that can cause compressions of magnetic fields. So this compressed magnetic field creates mirroring in MHD turbulence that can reverse the cosmic ray moving direction and cause their confinement in space. That explains their slow diffusion in star-forming regions indicated by different gamma ray observations of supernova remnants, of pulsar nebulae, and even molecular clouds. So with mirroring considered, we have the scattering of by faster modes. This has been studied also for 20 years in the literature, but now we know that the scattering by faster modes should be modified by taking into account the mirroring effects. Now, this can help us solve several theoretical problems and give also better agreement with observations. And this can be quite promising for us to understand, for example, the diffuse gamma ray emission in the galaxy. Okay, so I will stop here and thank you very much. I'm happy to take questions now.
Thank you, Siyao. Thank you. That was a great talk. Very nice summary.
Mm-hmm.
So we have the floor open for questions. Evgeny, do you want to start?
Thank you for the talk. It was good, very nice. I didn't manage to follow 2 points. One is when you presented the diffusion coefficient, if you go back, there is a dependence of the diffusion coefficient on the pitch angle. Not here before this.
Now this?
Yeah, this one.
Yeah.
How this should be understood? Pitch angle changes as the particle moves along the magnetic field in the magnetic bottles. The pitch angle changes. There is also scattering in the pitch angle. So what does it mean, this dependence? What is mu here?
Yeah, so this is a very good point. Let me try to explain. So for particle at a given pitch angle, if they are affected by, if this pitch angle is sufficiently large, it is subject to mirroring. But we know that for MHD turbulence, we not just have a single scale mirrors. We have the whole bunch of mirrors at different length scales following this energy cascade. And among these different mirrors, which mirror is most effective in reflecting this particle? And this problem was in fact studied already in 1970s by Cosworth and his collaborator. To satisfy the mirroring condition, there's a loss cone of pitch angles. So the largest pitch angle for the particle to be subjected to the mirroring effect is the square root of a delta B or B. So it depends on the magnetic fluctuation. So then we know given a particular mu, we have the most effective mirror happening when the magnetic fluctuation at that length scale is corresponding to this condition that I said, mu equal to square root delta B over B. So that is the mirror which is most effective for reflecting this particle. And the mean free path here is defined as the intervals, the distances of the particle going back and forth in the parallel direction. So here, for example, so between its returning its moving direction, reversing its moving direction. So this interval along the local magnetic field, this is in fact given by the scale of this turbulent eddy, which is mostly efficient reflecting the particle that we already theoretically know. So this is how, by using the faster mode scaling or slow mode scaling, we can easily get a dependence of this mu of this parallel diffusion coefficient. So this has been done analytically in our paper, Lazarian issue 2021. Now we have this already numerically tested. I didn't show it here, but this is mu dependence of the pitch diffusion coefficient now has been numerically tested.
So mu is the pitch angle for the particles which are most efficiently affected by those mirrors. Is this the meaning of this mu? Okay.
Yeah, so this mu, for example, in any simulation, you can give an initial mu of the particle. You can give, let's say, 0.8 or 0.7. And if you give this initial particle, it has the corresponding mirror size that is mostly efficiently can interact with this particle at this given mu. So if you start particles with different mu, you will observe different parallel mean free paths. So their motion between the mirrors will be different.
I see. And then the second question is, I'm not sure whether it will really apply to the situation, but this really comes to my mind, because in the similar situations, you may expect something like this. Imagine that you have magnetic bottles which efficiently confine particles until those particles, due to scattering over pitch angles, they go into the lost cone and escape from the mirror, and then they go to another mirror and got trapped there for quite a long time, etc., etc. This is diffusion. Then imagine that you have a series of magnetic bottles all along the magnetic field line. And by chance, a particle attains a very small pitch angle, so it just goes through all the mirrors. And this is not a diffusion. This is what is usually called Levy flights. And this is known to affect diffusion quite significantly in many situations. I wonder if this may happen here.
So this is really excellent point. Yeah, I forgot to mention that exactly. So you can see that, for example, here particle, this part is scattering, and this is mirroring, and scattering, mirroring, scattering. So it's so scattering has large diffusion coefficient, the mirroring has small diffusion coefficient. Indeed, this is a Levy flight-like motion of the particle. So if we talk about,
and then it's not really a diffusion. I mean, if you have Levy flights, then you don't have the diffusion, typical diffusion law that the square of distance, of average distance, is proportional to time. Then it's not like this in presence of Levy flights. So it's not really diffusion.
Right. So this is another new open question that we need to face now. So everything I talk about here, I didn't consider the combined effect yet. I was talking about, when I say mirror diffusion, I was talking about when the mirroring condition is satisfied. When I talk about scattering diffusion, I was only talking about this part. So when we put everything together, it is a Levy flight. And as you said, we shouldn't use a diffusion coefficient because it's not a mathematically or physically correct description anymore. And all this traditional picture for describing this Fokker-Planck equation, everything should be also updated. So this is something, we need to work on next. Yeah.
Thank you.
Thank you.
Yuri, please go ahead.
Hi, I apologize. Maybe it's a very naive question, but I was wondering if you have a mirroring at the point or at the turning point, the particle moves, but the particle doesn't move along the magnetic field, and it moves perpendicular to the magnetic field. So this would suggest that at locations of mirrors, you would have first of all much higher concentrations of cosmic rays, and second of all, they would all be moving perpendicular to the magnetic field. Do you expect, because of this, that locations of the mirrors would have brighter, let's say, synchrotron emission or other types of emission, and also with a certain polarization at those locations, or is it completely unresolvable?
Okay, so for the first parts of your question, okay, so in this mirroring region, because the scattering is so scattering rate is lower than mirroring rates, so we can safely believe the first adiabatic environment is well conserved. So in this case, if we ignore scattering, there's no pitch angle change. So we do not really expect that the particle would suddenly change the pitch angle, as you said, at the mirror point. So it will be still the pitch angle what we gave initially. But then if we talk about the accumulation of the particles near the mirror point, that is true, because particle, when close to the mirror point, they slow down until the velocity becomes zero, and then they reverse. So this accumulation effect is quite important. I haven't thought about in terms of emission, enhanced emission in space, but this has a quite important application to explain the accumulation of pickup ions near the mirror point, to explain the ibex ribbon that's in the heliosphere. So yeah, but yeah, for the emission, I haven't thought about it. I mean, we probably need to resolve individual mirror to see this effect. It's probably more challenging to do in the interstellar media. Yeah.
And the polarizations?
Polarization, yeah, so that is another question, because near the cosmic ray sources, all the scattering particles with small pitch angles would leave the source very quickly. So we expect some anisotropic distribution particles near the source with preference toward large pitch angles. So if all particles are relatively, well, with large angle with respect to the magnetic field near the source, I think indeed that may cause some effects on the polarization. Yeah, I haven't thought about that. I think it's a very nice point.
I think that we're, sorry, Yuri, did you have another question?
No, that's it.
Yeah, I had a question about the slide that you showed on IC443. And you had, so it showed the data that was taken by, yeah, this one, I think. You had another one, but they're similar. This includes both the Fermi lat data as well as the TeV, I think, right? I mean,
yeah.
So the point here is, what is, can you just explain one more time? Sorry, I missed this part. So the black line is a model which uses, so how are you getting, yeah.
So, okay, so this black line and the blue line, I use exactly the same parameters like density, magnetic field strength, initial injected particle spectrum. Everything is the same, except the diffusion coefficients are different. So the blue line, I use this average galactic value 10 to 28, I think centimeter square per second for GeV particles and beyond, following the 1/3 power law. This is empirical average galactic value. And the black line, I use the mirror diffusion coefficient. Yeah, so only the diffusion coefficient is different.
It's different, but the gamma rays are produced by leptonic, or is it also including a hadronic component? And
it's only right. It's only hadronic scenario considered here, because the source, they believe it's quite confident that it is hadronic source. So yeah, I only model the proton spectrum and the corresponding gamma spectrum by PP collation. Yeah.
And have you tried this on some of the other well-measured, like CASE, for example, is another example of a well-measured spectrum, also by Fermi, right?
Right. I look at another one, I think W44, but other, there are like a 10-ish, they have quite similar steep spectrum. I haven't looked at that yet, but I think they generally suggest slow, small diffusion coefficient in such type of sources. Yeah.
Okay, thank you.
Thank you.
Any other last questions? If not, I would really like to thank you, Siyao. That was a really nice talk. If you could send me the PDF, I would like to post it on the website.
Okay. Thank you very much.
And just want to remind everyone that in 2 weeks, we have the last talk of this session, and then we will continue in the fall. And the next speaker will be, I think it's, what is the name? I forget the title of the talk, but the talk will be given by Glenys Ferrar, and it'll be on cosmic ray and review. So looking forward to seeing everyone there. Thank you.
Thank you very much, Siyao.
Yeah, thank you, everyone. Bye.
Bye.